All right, so picture this. You've got a glass of water, perfectly still, and you drop in, I don't know, a drop of food coloring. You know, the kind you use for baking.
Oh, yeah.
Starts to spread out, right? Looks kind of cool.
Yeah.
But it turns out that simple process, it's like a gateway to some serious math.
Oh, for sure.
Some serious physics. So today, we're gonna dive into how scientists actually quantify that spreading, that diffusion. We're gonna use a sphere as our model, and trust me, it gets surprisingly complex.
I bet.
But here's the cool part.
Yeah.
This isn't just some, theoretical exercise.
Right.
It's got real-world uses.
Oh, yeah.
In all sorts of fields, like chemical engineering, understanding how pollutants spread, all that kind of stuff. So
it's really fascinating how something that seems so straightforward, like just watching something spread out, can lead to, like you said, intricate mathematical descriptions.
Yeah, exactly. So let's start simple, okay? Like, how do we even begin to describe something like a dye spreading in water? I feel like there's got to be an actual law for this, right? Like some scientific principle.
Oh, absolutely, there is. It's called Fick's second law.
Fick's second law.
Yeah, and it's kind of the foundation for understanding diffusion. Essentially, what it says is that substances move from areas where they're highly concentrated to areas where they're less concentrated.
Okay, so like they want to even out.
They want to spread out, yeah, exactly, until they're evenly distributed. They're trying to create this kind of equilibrium.
Gotcha. So it's all about like achieving uniformity.
Exactly, yeah. And the driving force behind all this movement, the thing that's pushing it all along, is the concentration gradient.
Concentration gradient.
Yeah. Basically, the steeper that gradient is, meaning the bigger the difference in concentration between 2 points, the faster that substance is going to move.
Makes sense. Okay, so where does the sphere come into play here? Like, how does that complicate things?
So imagine you've got a solid sphere, okay? And on its surface, there's a certain concentration of some substance.
Okay.
And it's submerged in a fluid, like water, right? And that fluid far away from the sphere has a different concentration of the same substance.
Okay, I'm picturing it.
And we're assuming that this is what's called a steady state situation.
Steady state, okay.
Which just means that things have been going on for a while, they're not changing rapidly.
Gotcha.
And to make things even simpler, we're only considering diffusion that's happening radially.
Radially.
So that's directly out from the center of the sphere.
All right, so everything's moving outwards in this uniform kind of pattern. Okay, so then how do we measure how fast this is all happening? Is this where the math gets heavy?
This is where it gets heavy, yeah.
Okay.
So to describe this process, we use something called the diffusion equation. Specifically, we use it in something called spherical coordinates.
Spherical coordinates. Okay.
Which sounds complicated, but the equation itself isn't really the key takeaway here. What matters is what it represents. Okay. Which is basically a way to calculate how the concentration of that substance changes as you move further and further away from the surface of the sphere.
Right. All right. I think I'm following. Now, you mentioned something earlier about boundary conditions.
Right.
What are those exactly, and why are they important?
Oh, they're really crucial. So boundary conditions, they basically define the specific limits of our system. Okay. So in our sphere example, we have two main boundary conditions. Right. One is that the concentration at the sphere's surface, that's fixed, it's a set value. And then the other is that far away from the sphere, the concentration is also basically constant, but it's at a different value.
So we've got these two set points.
Exactly. And these conditions, they help us tailor the solution to this specific problem.
Gotcha. All right, so we've got our equation, we've got our boundary conditions. What's next? Do we actually solve for this?
We do. Yeah, we solve it.
Okay.
And by solving the diffusion equation with those specific boundary conditions, we get a new equation.
Right.
And this equation, it describes how concentration changes as you move away from the sphere.
Okay. And so that lets us calculate
that lets us calculate something called the flux.
Flux, okay.
Which is basically the rate at which that substance is moving across the sphere's surface.
So how much stuff is flowing out per unit of time?
Exactly.
Yeah, okay. But how does this diffusion rate, how did that compare to how fast the substance would move if the fluid was actually flowing past the sphere? You know what I mean?
Yeah, that's a good question. So to compare those two things, we use something called the Sherwood number.
Sherwood number.
Okay. Yeah. It's a dimensionless number.
Dimensionless?
Meaning it doesn't have any units.
Okay.
And it basically tells us how much faster stuff is moving due to diffusion compared to if the fluid was just still.
Gotcha. So in our simple scenario with a still fluid,
right?
What's the Sherwood number?
It's 2.
It's just 2.
Yeah.
Okay. That's surprisingly simple. Is there any deeper meaning to that number?
It is simple, yeah. It's just this really neat way to encapsulate this whole situation into a single value.
Gotcha.
But things do get a little bit more intricate.
Okay.
And honestly, I think even cooler when the fluid is actually flowing past the sphere.
Okay, now we're talking. So what changes when the fluid is moving?
Well, the Sherwood number equation, it gets more complex.
Right.
You have to account for things like turbulence in the flow.
They're doing so.
And that's represented by something called the Reynolds number.
Reynolds number.
Or yeah. So the Reynolds number.
Wait, Reynolds number? Turbulence.
Yeah.
Didn't we talk about that when we did our deep dive on airplane wings?
Exactly.
It's like it pops up everywhere.
It pops up everywhere in fluid dynamics. Yeah.
When you're talking about fluids.
Yeah.
Okay.
And then there's another really crucial factor that comes into play called the Schmidt number.
Schmidt number.
Or Schmidt.
Okay.
And this one relates how easily momentum spreads through the fluid compared to how easily the substance that we're interested in, how easily that diffuses.
So momentum is like about the fluid itself.
Yeah, the fluid's movement.
And then diffusion is about the stuff within the fluid.
Exactly.
Okay. Speaking of substances that don't move very fast.
Yeah.
I was spreading cold honey on toast the other day, and it took forever, it felt like.
Oh, I know that feeling.
Like the honey molecules were just moving in slow motion.
Yeah, they're sluggish.
Yeah.
That's actually a great analogy. So a high Schmidt number means that momentum spreads through the fluid way faster than that substance diffuses.
Okay, just like my cold honey.
Just like your cold honey, yeah.
Gotcha. All right, so then how do all of these, like the Sherwood, the Reynolds, the Schmidt, how do they all fit together in the final equation?
So the equation for the Sherwood number, when we're dealing with flow, it takes all of these factors into account.
Okay.
It combines the flow characteristics, which are represented by the Reynolds number, with the properties of the fluid and the properties of that diffusing substance, which are represented by the Schmidt number.
Okay. So what does all this mean, like practically? Why should we care about these numbers and equations?
Well, this kind of analysis is actually essential for understanding all sorts of real-world processes.
Okay.
I mean, think about how pollutants disperse in a river, how chemicals react in industrial settings, or even how nutrients are transported in biological systems. It's all about movement.
It's all about movement and how fast things are moving.
Right.
So by understanding diffusion and by understanding how to mathematically model it, we can design better systems, whether it's for cleaning up pollutants, creating more efficient chemical reactors, or even developing new drug delivery methods.
Wow. It's amazing to think that something as seemingly simple as a drop of dye spreading in water can lead to this incredibly powerful way to describe and predict how things move and interact in the world.
It's really fundamental.
Yeah, it makes you wonder what other innovations might be possible by understanding these principles at such a fundamental level.
Absolutely. I mean, that's the beauty of scientific exploration.
Yeah.
You know, the world of fluid dynamics and mass transfer, it's vast.
Yeah.
There's so much more out there to discover.
For sure. Well, on that note, we're going to have to wrap things up for today.
But thanks for taking us on this journey into the surprisingly complex world of diffusion.
Oh, it was my pleasure. Glad to be here.
And until next time.
Until next time.
Keep those brains churning. Think about those drops of dye.
Yeah.
Spreading out.
Fascinating stuff.
Fascinating stuff.
Indeed.
All right. Take care.
You too.